This is Jack Creel, and I'm going to be discussing some of the common boundary conditions we use when we're talking about microscopic fluid flow. So the first one we can discuss is the no-slip boundary condition, which occurs at a fluid-solid interface and essentially just states that the velocity of the fluid is going to have to be equal to the velocity of the solid at the interface. And so this is because, as the name suggests there, the fluid particles aren't going to slip at that solid interface. So you can think of this as those fluid particles kind of being stuck to the wall at that point. So there's going to be no relative movement between the fluid and the solid. So the shared solid liquid velocity that we're going to see at these points is commonly going to be zero if we're talking about fluid flow through a stationary pipe or some stationary object. So that can be really helpful. The next one we'll talk about is symmetric flow. And that can exist in all sorts of things like pipes, channels, ditches, anywhere where the velocity profile of the fluid is going to have some sort of symmetry. So when we have this symmetric velocity profile, like you can see here, we know that the velocity gradient is going to be zero. It's not going to be changing at the point of symmetry, which in this case is this maximum velocity here. And so at this point, the radius is zero here because we're right at the center of the pipe, and the first derivative of the velocity isn't going to be changing. That's what we mean when we say the gradient is zero. So you can see that written out here at the point where the radius is zero, right at the center. There's no change in velocity with respect to radial distance. So the last boundary condition we'll discuss is the continuous shear stress that occurs at a fluid-fluid interface. And so this states that when we have adjacent flow of two immiscible fluids, you can see here there's two fluids flowing adjacent to each other. They're both going to experience the same shear stress at their interface. So we can see that expressed mathematically over here. The viscosity of one of the fluids times the velocity gradient is going to give the shear stress. And so that shear stress for one fluid is going to have to equal that shear stress for the other. So taken for the specific case of a liquid-gas interface, where the gas's viscosity is going to be really low, this boundary condition can tell us that the velocity gradient of the liquid will be zero at the interface. And so we can see that up here, because if one of these viscosities is really low, the only way that this equation is going to work out mathematically is if the velocity gradient of the other is really low. And so we can just say that it's zero for the velocity gradient of the liquid at that liquid gas interface.